Hello and welcome back to Abstract Linear Algebra, the video series where we talk a lot about general concepts from linear algebra. And it turns out that these things can be used in other parts of mathematics as well, so it's really worth learning them. For example, our orthonormal bases occur in a lot of fields. And in today's part 19, we will explain more about them. In particular, we will explain what the name Fourier coefficients means. But it might not surprise you that at the start here, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And if you really want to learn the content of today, it might be helpful to check out the link in the description to download additional material for the video. Okay, then let's immediately start with our setup from before, where we have a subspace in a vector space with an inner product. So V is our general F vector space with an inner product, and U our finite dimensional subspace in V. We do that in this setting because often we are interested in orthogonal projections. You might remember that every vector x in V can be projected in an orthogonal way onto the subspace U. And indeed, with the last videos, we've already solved this problem. So now we can calculate this orthogonal projection. And you also might remember that the common name we choose for this vector in U is x restricted to U. And moreover, we know how to calculate this orthogonal projection if we have an O and B in U. So let's recall this formula for x restricted to U. And to write this down, we just need an O and B for our subspace U. Indeed, the formula here is really compact in that case. Namely, we just need the sum from 1 to k, and then we just have the vector bj together with the inner product bj with x. In other words, in order to find the orthogonal projection, we just have to calculate these coefficients here. In fact, these are just scalars in our field F, and therefore this is a common linear combination, just written in a non-standard way. Hence, this formula helps finding the correct linear combination even in the case that x already lies in the subspace U. Obviously, in this case, the orthogonal projection of x is equal to x. But of course, the formula still holds. So maybe let's sketch this case. Now we just have to consider the subspace U. And inside U, we find our nice basis vectors from B, which are mutually orthogonal and also normalized. So every vector has length 1. And now our vector x also lies in U, which means it can be represented by a linear combination with the vectors from B. And you know, this is a common problem in linear algebra. To find the coefficients of a linear combination, we have to solve a system of linear equations. However, having an inner product and an O and B makes finding these coefficients ridiculously easy. In fact, we already know the formula for this, so we can summarize our result here. This is a very general result you should remember because it holds in any vector space with an inner product. In fact, one can even generalize that to infinite dimensional subspaces U. However, this is not something we do in linear algebra. This is more suitable for the functional analysis course. Therefore here, our orthonormal basis of U has k elements. And then we can say that for each vector U in U, we have a linear combination with the basis. And the coefficients here are exactly given by the inner product bj with U. Hence, in the case of an O and B, we don't have to solve a whole system of linear equations, we can just calculate inner products. And this is so nice that sometimes this linear combination gets a special name. It's called the Fourier expansion of U with respect to the orthonormal basis B. Often, the name Fourier is used in a very special context, but it can also be used for this general formula. And in this case, the scalars from the field F are called the Fourier coefficients. So please don't forget, we either have real numbers or complex numbers. Okay, then I would say we are ready to look at an important example for these Fourier coefficients. And in fact, it's not so simple because we have to deal with functions. So here we live in a function space, but I want to take a finite dimensional one. And therefore, there's no need to distinguish between v and u, so we can set them as the same vector space. And now in order to keep it simple, let's say we have a span of functions in our common function space. And for the first function, I want to have the constant function given by the constant 1 divided by the square root of 2. And then the second function should be the standard cosine function. And maybe the next one here is not so standard, it's the cosine function with a factor 2 inside. And then finally the last one is just the common sine function. And now you should see this is just a well-defined subspace in our real vector space f of R, which is the space of all functions from R into R. Okay, and now on this vector space V, we can define an inner product. Hence, we have to put in two functions f and g, and you might already know that an integral can help for the definition. In fact, we could say we have the factor 1 divided by pi times the integral from minus pi to pi. And then we simply have the product of f and g inside the integral. And now it's not hard to check that this is a well-defined inner product on V, which implies that we can calculate all possible combinations of vectors in this span. For example, having the cosine in both arguments of the inner product gives us the following integral. Not so surprising, we have the cosine squared inside. Now, this integral can be solved by integration by parts. I don't want to do it here, but I show you the result because it's easy to remember, it's just pi. Hence, the whole inner product gives us 1. So we conclude that this vector here has norm 1 with respect to this inner product. So the idea here is that we actually already have an O and B. And maybe for this, let's also check the cosine and the sine in the inner product. So there, inside the integral, we find an even function, the cosine, and an odd function, the sine function. And multiplying them gives us an odd function again, which means that the graph of this function has a nice symmetry. In particular, it's mirrored with respect to the origin. Therefore, since we integrate over a symmetric interval here, the areas will cancel out. So without much calculation, we can already conclude that we get out 0 here. So we have orthogonality between these two basis vectors. And now we have to do it for all the other combinations as well, and what we get out is indeed an O and B. So maybe let's call it B as before, so this is our O and B. Of course, we say O and B with respect to this chosen inner product. And therefore, this constant here is important to set the length of the cosine function or the sine function to 1. Okay, and now for our example, we want to calculate the Fourier coefficients for a function. So let's take a function u given by u of x is equal to sine of x squared. So maybe it does not look like it, but it's actually spanned by the basis vectors, so it's an element in our vector space V. And with that knowledge, we also know that we have an easy method to calculate the coefficients of the linear combination. In other words, now we calculate the so-called Fourier expansion of this function. This means we have to calculate exactly 4 inner products. Okay, then let's immediately start. The first basis element B1 is the constant function. Hence we have this constant and sine squared inside the integral. And there the calculation works exactly like for the cosine squared from before. So what we get out is pi times the constant. And pi cancels out again, so only the constant remains. Okay, there we have it. This is the first Fourier coefficient. Then let's immediately continue with the second one, where we have the cosine involved. So we have cosine and sine squared inside the integral. And this is really nice, because we can immediately put in an antiderivative. Namely, take sine cubed divided by 3. Then you know, for the derivative we need the chain rule, so we get out the sine squared, and also the inner derivative as the cosine. And now comes the thing, we have to evaluate it at the limit points. And then we don't need to do much, we immediately see that we get out 0. Simply because of the fact that sine at pi and sine at minus pi are exactly the same values. Okay, so this coefficient is 0, so let's go to the next one. There we now have the cosine with 2x inside the integral. Indeed, this is a longer calculation, so I tell you what comes out. This integral is minus pi half. And therefore the coefficient is minus 1/2. Okay, and with that, only one coefficient remains. And in fact, this one is easy again, because we can combine two sine functions. More precisely, inside the integral, we have sine cubed. So again, it's an odd function, and therefore the integral has to be 0. Okay, there we have it. We have all the 4 Fourier coefficients, and therefore the whole linear combination for this function. So let's state this as our result. In the abstract notation, we just have u is equal to b1 times the first coefficient plus b3 times the third coefficient. And there we know b1 is the constant function and b3 the special cosine function. Hence, we can write sine of x squared as the following sum. So first we have the constant function b1 times the coefficient plus the cosine of 2x times this coefficient. And there you see, we can put it together and write it as 1/2 times 1 minus the cosine of 2x. Okay, and there you see, this is how one can use the Fourier expansion to find the linear combination of functions. And indeed, this example was already a very special case which is important and known as Fourier analysis. I have a whole video course about that deals with the sine and cosine functions, so you can check that out. Here, of course, in abstract linear algebra, we want to keep it more general. Therefore, this is just an example, and we will still deal with abstract vectors here. And in the next video, we will see how we can always create an ONB with the so-called Gram-Schmidt procedure. So I really hope we meet there again, and have a nice day. Bye bye.